हाँ जी, अस्सलाम वालेकुम। तो चलें, let us start with today's lecture. And just to recap what we have done, we have done the forward and reverse biasing configuration of a diode. We have done the approximate and ideal semiconductor models of a diode. Then we have done a number of examples. Then we did the parallel and series parallel configuration. We sorted out some examples related to series and parallel configuration. Then we did the AC to DC rectification using single diode or the full wave diode bridge network or the center tapped transformer based bridge network. Then last time we discussed the ripple voltage. The ripple voltage is the outcome of using a diode to rectify AC to DC without capacitor. Ripple voltage is also present when we use a capacitor, but it will be improved. Our ideal ripple voltage is 0. This is the formula for ripple factor. And today, in today's lecture, we will start with the capacitive filtering. This is a technique to reduce ripple voltage by using a parallel or a shunt capacitor. So the introduction is that most practical electronic circuits require a DC voltage source that produces and maintains a constant voltage. For that reason, the pulsating half sine wave must be converted to a steady DC level. A steady DC level means that we need a straight line. And this conversion is accomplished by filtering, by something known as filtering the waveform. Filtering is a process in which selected frequency components of a complex waveform are rejected, or that is, they are filtered out so that they do not appear in the output of the device. The pulsating half sine wave, like all periodic waveform, can be regarded as waveform that have both a DC component and AC components. So let us take one half wave rectifier. We have a sine input, then we have a diode and a resistor. The input will be our regular sine wave, sinusoidal waveform. It will have one normal positive half and one normal negative half. And when this waveform is provided to the diode simply rectifies the diode will simply rectify the positive half. However, the problem lies in the output waveform. The output waveform should be steady. It should be a steady DC level. This is not steady. It is a half sine wave, then 0, then another half sine wave, and then 0 again. This is not steady. We need a waveform that should remain almost constant with respect to time. Right. So आगे चलते हैं. Our purpose in filtering these waveforms for a DC power supply is to reject all the AC components. It can be shown that average DC value of a half wave rectified waveform is given by V average is equal to VPR divided by pi. This is valid only for half waveform, where VPR is the peak value of the rectified waveform, and it is equal to under root 2 multiplied by the RMS value of the input voltage, minus 0.7 due to the drop. This average or DC value is what a DC voltmeter would read when connected across the load resistor. जी तो any question up so far? Now to get this filtering, the simplest kind of filter that will perform the filtering task we have just described is a capacitor. This is the simplest filter. A simple capacitor is our simple filter. We recall that a capacitor has a reactance inversely proportional to the frequency. That is, the impedance of a capacitor is equal to 1 over 2 pi FC. 1 over 2 pi FC. Thus, if we connect a capacitor directly across the output of a half-wave rectifier, the AC component will see a low impedance part to the ground and will not therefore appear in the output. The impedance of the capacitor is described by 1 over 2 pi FC. So larger the frequency, the smaller will be the impedance faced by that signal, and therefore it will pass through, large frequencies will pass through the capacitor. In figure 3.18, if a filter capacitor C connected in this way, here is figure 3.18, and we see that we have a normal AC input voltage, a diode, and output voltage, and then we have the capacitor connected across the load. The output voltage is given by expression V peak minus 0.7 volt. So whatever is the peak voltage of the input, this is V peak voltage of the input minus 0.7 drop due to the diode. The subtraction or the result of this gives us the output voltage. And the capacitor charges to the peak value of the rectified waveform, so the output is the DC voltage, VPR. Note that VPR is equal to VP minus D, where VP is the peak voltage and VD is the DC drop of the silicon diode. And then in practice, a power supply must provide DC current to whatever load is designed, it is designed to serve. And this load current causes the capacitor to discharge and its voltage to drop. The capacitor discharges through the intervals of a time between two input pulses. Each time a new input pulse occurs, the capacitor recharges. Consequently, the capacitor voltage rises and falls in synchronism with the occurrence of the input pulses. These ideas are illustrated in figure 3.19. The output waveform is said to have ripple voltage superimposed in its on its DC level VDC. So here we have figure 3.19, and here we have the performance of our power supply with capacitor, with the filter capacitor. This is the input voltage, the diode, and the capacitor. Before the capacitor, the input voltage will have looked like this, that there is a positive sine wave, then zero, then another positive sine wave, then zero. With the addition of the capacitor, what we get is we get a ripple voltage which is superimposing on the DC voltage. So here is the DC, this is the DC voltage, this is the regular DC voltage, and also this AC component. This AC component is the ripple voltage superimposed on the DC. And this is our new ripple voltage. And when we take the average of the new ripple voltage, we get this straight line. So first, without the capacitor, this was our output voltage waveform with too much ripple voltage. With capacitor, with the addition of the capacitor, we are now over here. That is, the output voltage has reduced the ripple voltage. Ripple voltage is, the formula is again V peak minus V minimum. The difference between the peak value of the output and minus the minimum value of the output is the ripple voltage. So if we had not used the capacitor, then where would the DC value, where would the DC value of the voltage lie? कोई इसका जवाब दे सकता है? So without using the DC capacitor, we must not forget that the DC voltage will be very, very small, almost over here, because we are taking the average of one cycle. And with using a DC capacitor, or a filter capacitor, our DC voltage also increases like this. It also increases. It also shifts to a higher level. So this is another advantage of using a capacitor. Now, a little bit formula that when the peak when the peak-to-peak value of the input of the output ripple voltage VPP is small compared to VDC, a condition called light loading, we can assume that the load current is essentially constant and will discharge the capacitor linearly according to the basic equation, that is delta V is equal to I delta T by over the capacitance, where delta I is the reduction in capacitor voltage over time. Delta V is the reduction in capacitor voltage over time, that is delta V is the ripple voltage itself. And delta T is the time during which delta V took place, and I is the current discharging the capacitor. Note that delta T within our discussion is very close to the period of the within our discussion is very close to the period of the rectified waveform. Therefore, replacing delta V with VPP, we can write the expression that VPP is equal to IL over FRC is equal to VDC over FRLC, where IL is the load, FR is the frequency, and C is the value of filter capacitance. So यहाँ पे in equation 3.12 what we have done is we have observed that in the case of a half-wave rectifier without a capacitor, the ripple voltage is essentially equal to VPP, the peak-to-peak output voltage. Okay? So delta V is replaced by VPP. Secondly, the delta T is the time during which delta V occurs, and this is essentially 1 over the frequency, or it is essentially equal to the time period. Therefore, delta T has been replaced by 1 over C. Delta T has been replaced by 1 over F, because 1 over FR is the time period. Therefore, we come to the new equation, equation number 3.12. And then the DC voltage across the load is the average of the maximum and minimum values caused by the ripple voltage. This can clearly be approximated as the maximum value minus 1/2 of VPP. That is VDC is equal to VPR minus VP by 2. तो ये जो इक्वेशन 3.13 है ये कहां से आ गई? This we will get by minusing the peak voltage rectified minus half of the peak to peak voltage. Or if we rearrange, we get VDC is equal to VPR minus IL over 2FRC. And here we should note that this form is expressed in terms of IL, which is the most general situation. However, in the case where the load is a fixed resistance RL, IL can be replaced by VDC over RL. This gives us VDC is equal to इसी इक्वेशन को आप सॉल्व कर लें. VDC is equal to VPR over 1 plus bracket 1 fraction 2FRLC bracket closed. So this gives us the introduction of ripple voltage and the filter that will reduce ripple voltage. Now, observing a rectified and filtered waveform, it is obvious that the smaller the variation VPP, the more the waveform will resemble a pure DC voltage. The variation proportion is known as ripple, and the value VP is known as the ripple voltage. Furthermore, the ratio of the ripple voltage to the DC or average voltage is known as ripple factor or percentage ripple, and represents a measure of how close the filtered waveform resembles a DC voltage. Obviously, low ripple factors are desirable and can be achieved by properly selecting the capacitor value. The ripple factor R is then expressed by BPP, that is the peak to peak or the ripple voltage divided by VDC into 100 to get answer in percent. Ripple factors of up to 10% are typically acceptable. So ripple factors from 0 to 10% are acceptable in non-critical application. However, precision electronic circuit would require power supplies with very low ripple factors. Although ripple factors could be reduced arbitrarily by using large capacitor, a more practical solution is to use special circuits called voltage regulators that not only reduce the ripple voltage substantially but also maintain a constant DC voltage under variable conditions. So यहाँ पे उसने कहा कि ठीक है ripple voltage जो है that should have a normal value for your normal regular loads. The ripple voltage should not exceed 10%. But for more precision power supplies, we need a lesser ripple factor. The capacitor is the best solution, but other techniques include voltage regulators. For example, voltage regulators like LM317. LM, ये model number है of 317. This is a example of voltage regulator ICs. Or you can also have a look at 7805. This 7805 is a voltage regulator that produces fixed 5-volt output, but the input voltage should be larger than 5 volt. LM317 on the other hand is a variable DC voltage. It produces regular, a steady, well-maintained variable DC output. So in this diagram, अब हमने just to cover what we have studied. Okay, in this diagram we see a sine wave input, we see a half wave rectifier, and then we see a load RL. The sine wave is rectified. The sine wave is rectified by the diode. The output voltage from 0 to t by 2 is a positive sine wave, then t by 2 to time t it is 0. And when we take the average is of a very small value. This shaded area represents the average value, and we can find the average value by performing the mathematics as shown over here. This gives us the average output value. Now, in order to reduce the ripple, and yes, we have a ripple voltage of this amount from maximum voltage to minimum voltage, and this is equal to V peak to peak. So So what we have to do is we have to reduce the peak to peak voltage and we have to increase the average voltage. इस average को आपने increase करना है और इस ripple voltage को इसको आपने reduce करना है. And this will be done by using a capacitor. So in this circuit, what we see is almost a similar circuit, but with the addition of a large capacitor. The capacitor will charge during the half time from 0 to t by 4. This is t by 4, this is 0. From time 0 to t by 4 to time t 0 to t by 4, this is t by 4 time 0. From 0 to t by 4, the capacitor will charge. The capacitor, it will charge like this. Then from t by 4 to time t, to this time, from t by 4 to time t, the capacitor will discharge. Then a time and then beyond time t, that is t plus delta t, we take this. Let us take this time t1. Then from time t to t1, the capacitor will keep on discharging because input voltage is small, capacitor voltage is larger, the diode is reverse biased. Therefore, the diode will not conduct and the current in RL will be supplied from capacitor C1. Then from time t1 to the maximum point, again the capacitor will charge. The capacitor will charge from time t1 to time t3. This is we call time t3. We call this time t3. The capacitor will charge from time t1 to t3. This is a very small window which the capacitor has just to charge itself. And during this time, large current will flow from the power supply into the capacitor. And for the remaining times, the capacitor will serve the output voltage. So during this time, we observe, from time t1 to t3, we observe that the output voltage increases. This increases because capacitor charges. Then from time t by 4 to t1, the voltage decreases because during this time capacitor is discharging. And here is the path where the capacitor is discharging. So when the capacitor charges, the voltage across the capacitor rises, and when the capacitor discharges, the voltage across the capacitor also decreases. And the net output voltage as seen by RL will look like this. This is the output voltage as seen or as observed by the load RL. If we had not used the capacitor, then the waveform seen by the load RL would have looked like this. This is the output voltage without capacitor. Without the capacitor, without capacitor C. And this is the voltage with capacitor. With capacitor C. So let us look into the let us look into the procedure of charging and discharging, and based upon this procedure, let us find the capacitor C. So let us look at the waveform and we will discuss the capacitance formulas. That is from time 0 to t by 2, we have a positive half wave. Then from time t by 2 to time t, we have 0 volts. Okay? Without using the capacitor, the V ripple is equal to VPP. That is the peak voltage of the input voltage, or maximum voltage of the input voltage minus minimum voltage of the input voltage. Then we see that the ripple voltage is too much large and we connect a capacitor. By adding a capacitor, what we have done is we have reduced the ripple voltage by increasing the V minimum. So in this waveform, what we see is that from time 0 to t2, for the first pulse only, from time 0 to t2, the capacitor will charge. Okay? And from time t2 to time t3, the capacitor will discharge. This will happen only for the first pulse. After the pulses continue, what we will see is that from time t1 to t2, the diode conducts. That is, current passes through the diode. This current passes through the diode. This current charges the capacitor and it serves the load during from time t1 to t2. From time t1 to t2, we have a current which is flowing into the capacitor from the power supply. And this is the reason why output voltage is increasing. We see an increment in the output voltage. Then from time t2 to time t3, the input voltage becomes less than the capacitor voltage, and our diode is reverse biased. Yes, even in the positive half, our diode is reverse biased because capacitor voltage is much larger than the input voltage. When the capacitor voltage is larger, our diode will become reverse biased. And now all the voltage will be provided by the capacitor. The capacitor will serve the current required by the load. And when the capacitor provides the current or serves the current, the capacitor loses its own charge. And therefore, the capacitor loses its own voltage. Therefore, we see a decrement in the output voltage, and this is the time when the capacitor is discharging up to time t3. At time t3, input voltage becomes larger than the capacitor voltage. The diode becomes conductive, and again we see a rise in the output voltage. And this is the time when the capacitor is charging and the load is being provided current from the power supply. And as a result, we see that the output voltage has now a lesser ripple as compared with the previous one. So to look into the mathematical dynamics, if we observe that charge removed from the capacitor during discharge, that is from time t2 to t3, is delta t is equal to IL into t. This is a quite straightforward formula. That is the current multiplied by the time gives us the change in charge. The current multiplied by the time during which this charge occurred gives us the total charge removed, where t is the time period of AC voltage. Here charging time t1 to here charging time T1 to T2 is very less compared to discharge time. Hence, we take time T. Now, yes, this in this formula we have made a approximation, and this approximation is that since the time from T1 to T2 is very small, very small as compared to time T2 to T3, therefore we will assume that the capacitor discharges in a complete cycle. And if VPP is the peak-to-peak ripple voltage and C is the capacitance, then delta V is equal to V peak-to-peak into C. This formula is our traditional formula that Q is equal to C into V. And if we equate these two formulas, we get, if we equate these two formulas, or if we equate these two formulas, then what we get is we get a capacitance value. C is equal to IL into time T divided by V peak to peak, and the unit is farads. So this slide demonstrates how to find the capacitance value. However, we must not forget that this capacitance, it will be a minimum value, and a minimum value will have a certain ripple. Now, to reduce the ripple, we should increase the capacitance. But as we increase the capacitor, we will observe another problem. That is that when we turn off the power supply, the capacitor will remain charged and our circuit will remain active as long as the capacitor is providing the current. Okay? So the best solution is to keep the capacitance small. And yes, and another thing is that the nature of the capacitor is always to use an electrolytic capacitor. That is, we need a capacitor
Was
of large value.
sorry to interrupt you, sir. But why do we always need electrolytic capacitor? Can't we use ceramic capacitor? They are easily chargeable, dischargeable.
The problem with
Electrolytic are capable of blowing up also.
the problem with ceramic capacitors are that they use too much volume for even a small value of capacitance. Electrolytic capacitors, they provide large capacitance in a smaller space, in a smaller physical volume. So this is the advantage. ठीक है? Okay जी. तो ठीक है जी. Now, just to summarize, summary of all rectifiers for resistive load is that in a half wave rectifier, we need one number of diodes. In a standard wrap rectifier, we need two number of diodes. In a full bridge network rectifier, we need four diodes. Then, secondly, center tap transformer is required only in center tap rectification case. For half wave and for full bridge network, we do not need a center tap transformer. The average DC voltage produced in a half wave case will be V maximum divided by pi. For center tap, it will be 2 times Vm divided by pi. And for bridge network, it will also be 2 Vm divided by pi. The peak inverse voltage for each diode, if we are using a half wave, then it is equal to Vm. If we are using a standard tap, then it is equal to 2 Vm. If we are using a bridge network, it will again be Vm. The output ripple frequency in the case of half wave becomes F main, that is whatever is the frequency of the power supply, we will have the same frequency. But in the case of standard tap and bridge network, it becomes twice the frequency because we are rectifying. And if I can draw over here, what we mean is that in half wave rectifier, our frequency is from 0 to pi, sorry, from 0 to 2 pi. But in standard tap transformer case, it is 2 times the frequency because the cycle repeats itself in both these cases. Therefore, the output ripple frequency is 2 Fm, or twice the main frequency. And if large electrolytic capacitor is placed across load in any of the above rectifier, it reduces peak. And if a large electrolytic capacitor is placed across load in any of the above rectifier, it reduces peak to peak ripple, and the average output voltage is almost equal to peak output voltage. So now let us come to an example. This is the statement of the example. That is the sinusoidal input IE in figure 3.19 is 120 volt VRMS and has frequency of 60 Hz. The load resistance is 2 kilo ohms and filter capacitance is 100 microfarad. Assuming light loading and neglecting the voltage drop across the diode, find the DC value of the load voltage. Find the peak to peak value of the ripple voltage. Here we have the circuit diagram of figure 3.19. The voltage supplied, this voltage is 120 volt VRMS, and the frequency is 60 Hz. The value of resistance RL is 2 kilo ohms and the value of capacitance C is 100 microfarad. We have to find the DC value of the load voltage. We have to find the DC value of the load voltage across RL, and then we have to find the peak to peak value of the ripple voltage. We have to find peak to peak value of the ripple voltage. So what we will do is we will use formulas 3.13 to 3.15 because 3.15 shows DC voltage equal to VPR, V peak after rectification, divided by 1 plus 1 over 2 FRRL. We are using this formula because in equation 3.14 we need the current, which the current is not provided. So we are using values of the resistance and the capacitance. Now, how do we find, in our example, how do we find VPR? The V peak is equal to under 2 multiplied by 120 RMS, because 120 is the RMS voltage. To find the peak value, we will multiply RMS. We multiply RMS voltage with under 2, and this is 169.7 volt. This is the maximum voltage. Now, 169.7 is very large compared to 0.7 volt of the silicon diode. Therefore, we can neglect or we can ignore the 0.7 volt drop of the diode. So this gives us a peak voltage. The DC voltage will become 169 divided by bracket 1 plus 1 over 2 FRL. And this gives us 162.9 volts. This is the DC voltage available across the output while using 100 microfarad capacitance. And then peak to peak value of the ripple voltage. How do we find the ripple voltage? We will find the ripple voltage by using equation 3.12. 3.12 is V peak to peak, which is essentially our ripple voltage is equal to VDC over FR, that is the frequency, into RL, that is the load, into C. So this is equation number 3.12, and we are using this equation to find the peak to peak value of ripple voltage. This is 13.57 volts. Okay, so any questions so far?
That the upper peak is not at the same level of the lower peak. Then what to do for this formula?
To make the upper voltage level equal to the lower voltage level. Can you please repeat your question? You want the lower voltage level to be equal to the upper voltage level?
Sir,
जी जी बोले.
suppose if there is a sine wave and it's higher peak value, higher and the higher peak value is 5, but the lower peak value is say -2. So then this formula will be applicable.
Can you please write your question in our conversations? I'm really facing difficulty in trying to listen what you want to say. अगर आप अपने कन्वर्सेशन में मुझे मैसेज कर दें कि क्या आपका सवाल है, then maybe I can respond.
सर
जी
VP हम 169.2 यही रखेंगे या इट मे बी वेरी
वी
VP
165 पर
169.2
जी जी
हम यही पुट ऑफ
नहीं
करेंगे सर इट कैन बी वेरी
यस हाँ जी ठीक है वो आपने 169.7 लेना है बिकॉज हम वोल्टेज ड्रॉप ऑफ द डायोड को इग्नोर कर रहे हैं उसकी दो वजूहत हैं पहली वजह तो ये है कि अगर आप स्टेटमेंट पढ़ लें कि निगलेक्टिंग वोल्टेज ड्रॉप अक्रॉस द डायोड एक तो ये वजह है और दूसरी वजह ये है कि 169 के मुकाबले में 0.7 volt drop of the silicon diode has a very small existence value. So we are ignoring such values for the fact that our calculations can be done easier.
Okay, sir.
So this is why we have ignored the voltage drop across the diode. But अगर आपको accurate result लेने हैं, then you can always take into consideration the voltage drop of the diode.
Okay, sir.
ठीक है so हाँ जी
सर एक क्वेश्चन
जी बोलें
वी मीन रिपल हमारी वेव्स हैं ऐसा ना
क्या कैसी वेव फॉर्म्स हैं
रिपल्स इट मींस कि रिपल्स हमारी वेव्स हैं जैसे पानी की सतह पे वेव्स बनती है ना सेम एज इनकी शेप ऐसे
जी
बन रही
जी
है ना सर तो
हाँ जी
उनको मिनिमाइज कर सकते हैं जैसे जितना हमारे वोल्टेज होंगे तो उतने हवाले से अगर वोल्टेज बढ़ते जाएंगे तो वो रिपल्स भी बढ़ते जाएंगे इज इट यस नो
वोल्टेज आपके इंक्रीज होते जाएंगे इफ यू चेंज द लोड
जी और सेम एज रिपल्स
yes yes obviously even if we look at equation number 3.12 को देख लें या 3.13 को देख लें या इवन 3.13 को देख लें कि RL का जिक्र सब में हो रहा है ठीक है ना so this means that the ripple voltage is a function of RL also but in practice we don't change RL too much for example if you have a resistor if you have a iron which is a resistive the value does not change the value RL does not frequently change so we need another approach to reduce the ripple आप ये कहना चाह रहे हैं कि जी आप ripple को reduce कर दें by increasing RL which is very possible it is very true but the value of RL is defined by the load itself अगर आप एक फैन लगाना चाहते हैं एक डीसी मोटर लगाना चाहते हैं तो जो डीसी मोटर की जो रेजिस्टेंस है वो यूजर तो कभी कंट्रोल नहीं कर सकता अगर आप उसकी रेजिस्टेंस बहुत ज्यादा कर देंगे जस्ट टू मेक रिपल वोल्टेज वेरी स्मॉल तो ठीक है रिपल वोल्टेज स्मॉल हो जाएगा बट द मोटर विल नॉट रन बिकॉज मोटर its required current. Therefore, we have to use other techniques to reduce ripple. ठीक है
ठीक है
जी जी पूछें
इसमें स्लाइड्स भी शेयर कर दीजिए
जी जी जरूर Any other question? Any other question from the students? So ठीक है तो next time we will meet in the next class. Thank you very much. Assalamu alaikum.